Welcome to the Problems Channel Season 2, Episode 23, the episode which I titled Euclidean GCD Algorithm via Scope Reduction, because in this episode we will precisely discuss how and why does the Euclidean greatest common divisor algorithm work if we look at it through the lens of the scope reduction problem-solving approach. Before I do that, however, as a traditional friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section find the episode titled The Problems Channel How To. Watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we motivate and explain everything that we do on this channel. I have framed the discussion of how the Euclidean greatest common divisor algorithm work in terms of a mathematical problem S2E23, and that problem is not a traditional problem in the sense that in this challenge we are not asked to generate our own solution, but instead we are asked to explain how does a solution generated by someone else work. Before we do that, however, I would like to establish the common language. Before we deep dive into the explanation of how and why does the Euclidean greatest common divisor algorithm work, I would like to establish the common language, because this episode is not an introduction to the elementary theory of numbers. We will cut to the chase and look at the practically most interesting and substantial material, and that is positive whole numbers greater than 1, because it gets very quickly very annoying to say and hear all the time strictly positive whole numbers greater than 1. Let us agree that for the duration of this episode, whenever I say the word a number or the numbers, I would mean exactly that, strictly positive whole number greater than 1. Thus, in order to understand how and why does the Euclidean greatest common divisor algorithm work, it is imperative that we have a good and firm grasp on the following notions. A strictly positive whole number greater than 1, p, is prime, shown over here, if it has exactly and only two positive divisors, the number 1 and the number p itself. The list of initial prime numbers is shown over here: 2, 3, 5, 7, 11, 13, 17, 19, and so on. That list goes on forever. The number of prime numbers is infinite, as was cleverly shown by Euclid more than 2,000 years ago, and the argument that Euclid used back then is quite elegant. If we assume, for example, that the number of primes is finite, then we construct a number that is a product of all primes, then we add 1 to that number, and then we see that none of the primes in that number divides that number. Of interest over here is the fact that 2 is a number that is even. That is the first, the last, and the only even prime. All the other primes are odd. A whole positive greater than 1 number, n, is composite, shown over here in red, if it has strictly and exactly more than 2 positive divisors. That list of composite numbers also goes indefinitely, forever. That list in infinite. The initial set of composite numbers is shown over here: 4, 6, 8, 9, 10, 12, 14, 16, and so on. For example, in that list, we grab any number. For example, 4, it has how many positive divisors? 3, 1, 2, and 4, and so on. Now, just to make sure that even though we will not be looking at numbers 0 and 1, again, to establish the common ground and the common language, 0 is a number that neither prime nor composite, and it is neither negative nor positive. Number 1 is neither prime nor composite for all sorts of fabulous historical reasons. Again, I'm not going to go into the long debate about why 1 is not prime number and why prime numbers usually taken to be positive. The people who came to watch this episode and who want to understand how the Euclidean greatest common divisor algorithm work most likely do not know about so-called commutative rings and so on. So for now, we stick with strictly positive numbers and numbers actually greater than 1. That's the most interesting, practically interesting, substantial case. Now, the next notion that we need to be familiar with is the so-called fundamental theorem of arithmetic, abbreviated over here as FTA. And according to the fundamental theorem of arithmetic, every whole positive number greater than 1 is either prime or composite, and in which case, if the number is composite, then it has a unique factorization over the set primes if the order of these primes in the prime portrait of a composite number is ignored. For example, if we take a number, just a sample, as such as 540, for example, it's not that difficult to decompose it over primes. This is the prime factorization of this number to which we refer as 540. We can call it a prime portrait, if you will, and instead of listing out every prime factor in that number explicitly, we can compress, use positive, shown over here without the plus sign, but we understand these powers are positive. So each prime can be compressed into a positive power, as shown over here. 2 to the second power, 3 to the third times 5. And again, courtesy of the fundamental theorem of arithmetic, modulo swapping the order of factors in this number to which we refer as 540, that list over here of primes shown on the board is unique. None is missing, and no more primes can be inserted over here in order and in such a way that the numbers 540 remains what it is. And it is interesting that all this information, prime, composite, fundamental theorem of arithmetic, is framed in terms of a notion known as a divisor. So here we say that a number A divides a number B if for the numbers A and B there exists a number C such that A times C is equal to B. Now, we design our numerical systems in such a way that all the arithmetic operations yield unique results. As such, perhaps one of the simplest way to ensure that the results of this definition are unique is to prohibit the division by 0. As such, we say that the number A not equal to 0 divides B if for the numbers A and B there exists a number C such that A times C is B, and in that case it is also evident that the number C shown over here is unique for this pair of numbers A and B. Now, from this definition it is also evident what? If the number A divides the number B, then the number negative A does what? Then the number negative A also divides B. We can show it over here, for example, as follows. If we write negative A like so, then from this definition over here, what can we say? Well, if we multiply it by negative C, then voila, we have our number B. And what does that mean? That means that the set of all the divisors of a given number can be obtained by a mechanical adjoining the corresponding negative divisors that are taken from the set of positive divisors. For example, the whole number 6 has the following set of positive divisors as designated by me over here with the plus sign: 1, 2, 3, and 6. Why is that? Well, for example, for the number, let's say 2, number 2 divides number 6 because for the numbers 2 and 6 there exists a whole number such as 3, which yields 6 when multiplied by 2. 2 times 3 is 6. So on, if we work through this definition, this is the set of all the positive divisors of the number 6. And the set of the entire or all the divisors of the number 6 is obtained, again, mechanically by adjoining to the set of all the positive divisors all the negative divisors that are obtained. How? Well, we take all the positive divisors, put the negative sign in front of it, and voila, we have our negative divisors. We unionize them or join them in a simpler language, and we have the set of all divisors of a given number. Plus minus 1, plus minus 2, plus minus 3, plus minus 6. This is the set of all the divisors of the whole number 6. Also of special interest is the fact that the number 1 divides every whole number. And what does that mean? That means that the set of all divisors of any whole number is never empty. And now that we discussed the basic points that establish the common language, we want to zoom in a little bit on the notion of a divisor of a whole number. Now that we know what a divisor of a whole number is, a natural question that comes up is the following. Can it so happen that one and the same whole number b divides two hopefully distinct whole numbers a and b? And the answer to that question is evidently yes, it may very well so happen. And if that happens, in other words, if a number d divides numbers a and b, then that number d is called a common divisor. For example, 3 divides 12 and 3 divides 24. Why is that? Well, because for the pair of numbers 12 and 3, there exists a number 4 such that 3 times 4 is 12. And for the pair of numbers 24 and 3, there exists a whole number such as 8, and 8 times 3 is 24. Consequently, in this case, we will say that 3 is a common divisor of numbers 12 and 24. However, if a proposed number does not divide at least one number in the pair, then that number cannot be possibly a common divisor of two numbers. For example, the number 8, it does divide 12. Why is that? Because for the numbers, for the pair 24 and 8, there exists a number 3 such that 8 times 3 is 24. But 8 does not divide 12. In other words, our definition, which has the symbolic form of 12 equals 8 times x, where x must be a whole number. Such an equation, if you will, does not have any solutions, or technically the set of solutions of that equation is the empty set, so no such integer exists. 8 does not divide 12. Consequently, the number 8 is not a common divisor of 12 and 24. Next, we remember from the previous segment that number 1 divides each and every number. That means that the set of divisors of any single number is never empty. It has at least one in it, and that also means that the set of common divisors of two numbers a and b is never empty. Evidently, 1 divides a no matter what a is, and 1 divides b no matter what b is. Consequently, if from the set of all the common divisors of two numbers a and b, we pick the largest by magnitude, that largest by magnitude common divisor will be called the greatest common divisor, or sometimes people say greatest common factor, if you will, it doesn't matter. We will stick with the terminology greatest common divisor, and in this case we will abbreviate as GCD, greatest common divisor, GCD. Now, for example, from the numbers that we worked with before, 3 is a divisor, 3 is a common divisor of 12 and 24. But is it the largest possible? The answer is no. Apparently, 12 is the divisor that is common for both numbers 12 and 24. 12 divides 12 and 12 divides 24. 12 is greater than 3, and 12 is the largest number that divides both. Consequently, 12 is the greatest common divisor of 12 and 24. But in an official or typical textbook definition of the greatest common divisor that you may see in various textbooks, there is a little caveat. Let's say two numbers in question are both 0. Then the notion of the greatest in terms of common divisors does not really apply. That's why I wrote here that there is no GCD, or no greatest common divisor, for such numbers. And it is relatively straightforward to understand why that is, because the set of, let's say, whole positive numbers is not bounded from above. And what that means is the following. Let's say we play the following game. You give me a number such as 1,337,000, and you claim that this is the largest common divisor of numbers a and b, both of which are 0. I take your number, add 1 to it, and the resulted number, your number plus 1, has the following two properties. That number is still a whole positive number, and it is a whole positive number that is strictly larger than the number that you gave me. Now, I claim that that number is the greatest common divisor of these two numbers. However, you take my number, add 1 to it, And that new number has the following two properties. That new number is still a whole positive number, and that number is strictly greater than the number that I gave you. Now, you claim that this new number is the greatest common divisor, and the point is that that game can go on forever and ever. It never ends. So in that sense, when both two numbers are 0, there is no point of trying to find the greatest common divisor of two zeros. That greatest common divisor simply does not exist, and that is why in a typical textbook definition of the greatest common divisor, we say that the greatest common divisor of two whole numbers a and b, not both 0, is a number, is a divisor of these two numbers that has the following two properties. Obviously, that number d divides a and b, and if a number c divides the numbers a and b, then the number c is less than or equal to d. Now that we understand how the notion of the greatest common divisor emerges, we already covered one special case. In the next segment, we'll cover a small number of similar special cases that we will not generally consider when we will discuss how the Euclidean greatest common divisor algorithm work. In order to zoom in on an algorithmically substantial and interesting material, we considered the following special cases when it comes down to the process of computing the greatest common divisor of two whole and positive numbers. The first case, when both numbers are 0, we already discussed in the previous segment. So from now on, we consider the cases when numbers a and b are not both zeros. That means that, for example, first at least one number may be 0 and the other one is not. Let us assume that the number a in the pair AB is 0 and b is not 0. Then the greatest common divisor, and here I switch to lowercase because if you will be writing this sort of information in LaTeX, for example, in LaTeX \GCD precisely stands for the built-in function, and the LaTeX rendering engine will nicely render the letters GCD in a way that looks like a function. So the greatest common divisor of two numbers, 0 and b, non-zero, will be, then we know right away, in most general case, the absolute value of b if we consider negative numbers too. But again, like I said, in general, right now we're interested in strictly positive numbers greater than 1, but to be pedantic, we can throw in the absolute value of b, and that fact should be understood because remember from the previous segment, we can play the ping pong of this number is the greatest common divisor of 0 and 0. No, that number plus 1 is greater, and so on. But here, that ping pong that never ends is stopped precisely by the magnitude or by the absolute value of b, or if we consider only strictly positive whole numbers greater than 1, this ping pong of plus 1 plus 1 plus 1 will be stopped precisely by the value of the number b, and it is evident that no number larger than b divides b over the set of integers. So in this case, the greatest common divisor of the numbers 0 and b not 0 will be b, and we know this information ahead of time. We do not need to carry out any computations. Likewise, if the number a in the pair is not 0, but the number b is 0, exactly the same scenario unfolds. The greatest common divisor of a not 0 and 0, again, will be the absolute value of a in general. But if we concentrate only on whole positive numbers, then the greatest common divisor of a and 0 will be a. Again, the ping pong of I'll give you this number, I add plus 1, I add plus 1, and so on, again stopped precisely by the magnitude of the number a, this information known to us ahead of time. So from now on, we consider the cases when not only not both numbers are 0, but we can also eliminate the case when one number in the pair is 0. Now we consider the third case when two numbers at hand are one and the same by magnitude, 3 and 3, 57 and 57, and so on. What will happen in this case? Well, evidently, again, if we consider all positive numbers, then the greatest common divisor of pair of numbers which have the same magnitude will be absolute value of a. If we concentrate only on strictly positive whole numbers greater than 1, then the greatest common divisor of a pair of numbers, each of which are one and the same, will be that value, a, the magnitude of a, because again, evidently, both numbers are a. None of the whole numbers greater than a divides a. Bam, the work stops over here. Again, we can draw this conclusion ahead of time. There is no computation, just basic reasoning based on the fundamental definitions. The fourth, so from now on, and from as we eliminate each and each special case, we take it that the scenario covered in this case will not be applicable in our work. So now we take on the case number 4, when either of the numbers in the pair is 1. I'm sorry, over here I misspelled. Sorry, this is, yes, this will be A, this will be B. This is A. If one of the numbers in the pair is 1, again, we know that no number larger than 1 can divide 1. The number 1 has how many divisors? The number 1 has precisely 2 divisors, -1 and +1. Across these two, 1 is obviously, the +1 is the greatest or largest by value. Consequently, 1 will be the greatest common divisor. And no matter what the value of the number b, for example, here, or a, 2, 3, 4, 5, and so on, these numbers cannot possibly divide 1. So 1, in a way, is a stopper that stops the show of computing the greatest common divisor of two numbers. The answer in this case, which is 1, again, is known ahead of time. So from now on, we take it that all these previous conditions are honored, plus no number in the pair is 1, because this case again is not interesting. The result is known ahead of time. The last condition, number 5, that I can think of is the fact that, for example, one number in the pair divides the other number, as we saw, for example, with the pair 12 and 24. 24 does not divide 12, but 12 divides 24. Obviously, the answer in the question to the question of what is the greatest common divisor of 12 and 24 is 12. So in other words, if in the pair of numbers a and b we have it that, for example, a can be represented as a product of b with c, then what does that mean? That means that when we calculate the greatest common divisor of such a pair, the largest number that divides b will be b itself, and b will obviously divide a, and hence the answer in this question will be B. And again, that case is not that interesting. We can compute and reason about all these cases ahead of time. There is no interesting, non-trivial, non-zero algorithmic work that can be done. That's known all ahead of time. Consequently, for the purposes of understanding how and why does the Euclidean greatest common divisor algorithm weaves its magic, we will take the following 3 basic assumptions. The numbers at hand, a and b, will be strictly greater than 1. The numbers will be distinct. None of the numbers divides the other. For example, as we saw in the previous case, 12 divides 24. 24 does not divide 12, but regardless of how the mix is given, it is not the case that one number divides the other, because again, the answer is known ahead of time. And without loss of generality, we will also assume, for the purposes of and for the sake of definitiveness of how we will be promoting different numbers into different numbers, we will assume that in our case, number a is always greater than number b. That can always be done, because if it's not the case, we simply swap the numbers and voila, a is greater than b without the loss of generality. And now, before we deep dive into the mechanics of how does the Euclidean greatest common divisor algorithm work, let us look at the kindergarten or childish way of computing the greatest common divisor of two numbers that is simply not going to fly. Back in middle school, I was told, and I'm pretty sure that all our viewers were told that information, again, back in middle school or maybe in high school, during the introduction to the elementary theory of numbers, that a way to construct the greatest common divisor of two numbers is to represent each number in its prime factorization, construct the corresponding multisets, take the intersection of these two multisets, and then multiply through all the numbers, all the prime numbers that made it into the set intersection. For example, to give a concrete scenario, let's say our number A is 525, is strictly larger than number B, that is 60. And in order to construct the greatest common divisor of these two numbers using the idea of the intersection of two multisets, each of which represents the prime factorization of the number at hand, we do the following. We write down all the prime factors of the number 525, shown over here, 3, 5, 5, 7. That is not too difficult to see. For example, 5 times 5 is 25, 25 times 3 is 75, 75 times 7 is what? 70 over 7 is 490, 7 times 5 is 35, 490 and 35 is precisely 525. Boom, there we have it. Number 60 is even simpler. 2, 2, 3, 5 are the prime factors of 60. That is easy to see. 2 times 2 is 4, 4 times 3 is 12, 12 times 5 is 60. Bam, we have the prime factorization of 5. Now, these constructs over here are called multisets. These are not sets, but technically multisets. And when we construct the intersection, shown over here with this funny sign here, when we construct the intersection of these two multisets, we basically take all the elements in each multiset that are present in both multisets. For example, we look at number 2. 2 is present in B, but is it present in A? No, so all 2's go out. Next one is number 3. We see that number 3 is present in the multiset B, it is present in the multiset A. Bam, 3, this copy of 3 makes it into the intersection of these two multisets. No more 3's are available. Now we grab 5. 5 is present in B, 5 is present in A, actually in 2 copies, but we have only 1 here. So 5 makes it into the intersection. We run out of the material in the multiset B. There is more material in the multiset A, 7, but 7 is not present in the multiset B. We claim that the intersection is constructed. Only 2 primes made it into this intersection, namely the prime 3 and 5. And now when we multiply this, or all the primes that made it into the intersection of these two multisets, bam, we have our greatest common divisor. That is, the answer to the question is, what is the greatest common divisor of the numbers 525 is 60, is precisely 3 times 5. And many people will say, oh, that is 15. So this process works, and perhaps it is even attractive theoretically, because we say things like multisets, intersection of multisets, sounds wonderful. However, that approach is absolutely hopelessly not practical, precisely because factoring large numbers, or real life large whole numbers, is computationally prohibitive. And the business of factoring large numbers in real time using even electronic computers is very laborious. That is not the way to do it. And amazingly enough, the algorithm that we have for the straightforward and fast computation of the greatest common divisor of two whole positive numbers was evidently put together more than 2,000 years ago. It is still in use, and that is the algorithm to which we refer as the Euclidean greatest common divisor algorithm, which we will look at next. The Euclidean greatest common divisor algorithm is an absolutely amazing algorithm that was invented more than 2,000 years ago, and it is still in use to this day. And to the best of my knowledge, in the Western civilization at least, even though we refer to that algorithm as the Euclidean GCD algorithm, it was not Euclid who invented this algorithm. Euclid apparently described that algorithm in his famous work Elements. But again, apparently, and to the best of my knowledge, in the Western civilization, it were the people who came before Euclid who actually invented that algorithm. Now, the heart and the soul of the Euclidean GCD algorithm is actually a chapter that is taken verbatim from the problem-solving approach that we're studying right now, the scope reduction problem-solving approach. Because instead of entering into the quite messy and laborious business of dealing with prime factors of the two numbers at hand, the Euclidean GCD algorithm quite elegantly subtracts the smaller number from the larger number repetitively, substituting one number into the other if needed, and I will explain that in a moment. What does that mean and how does it work? And that consecutive subtraction keeps going until 0 is reached, and at which point, as an immediately previous non-zero result, voila, the greatest common divisor of two numbers at hand emerges all by itself and as if by magic. And the interesting thing is that all along this reductive journey of making a consequent problem simpler and simpler, the Euclidean GCD algorithm stays true to the spirit of the scope reduction problem solving approach. I explained how that approach works in season 2, episode 21. If any one of you guys missed that episode, you may want to watch that episode again to see how the scope reduction problem solving approach works. But in its step-by-step iterative subtraction process, the Euclidean greatest common divisor algorithm, when I say that it stays true to the spirit of the scope reduction problem, I wrote these two main points of that approach on the board, so you guys not only hear it from me, but you can see it on the board. So at each and every iterative step, the Euclidean greatest common divisor algorithm reduces the perceived complexity of the problem at hand by genuinely reducing the size of that problem, and while doing so, that algorithm also preserves the technical essence of the original problem in every simplified problem. And when we say that the Euclidean GCD algorithm preserves the technical essence of the original problem in every simplified problem, what does it mean? Well, technically, when we say that the Euclidean GCD algorithm at each and every iteration preserves the technical essence of the original problem at hand in every simplified problem, simply means that in each and every simplified problem, the magnitude of the greatest common divisor of two numbers at hand is preserved. It is one and the same, and it is not altered in any way, shape, or form. In addition to being of interest in its own sense, the greatest common divisor also enters into this beautiful relationship that I shown over here. This is another little theorem from the elementary theory of numbers, and it states that the greatest common divisor of two numbers a and b, when multiplied with the least common multiple, or LCM, of two numbers, yields precisely the product of these numbers at hand, a times b. Overall, the greatest common divisor of two numbers finds its application. I know that people are always interested, what is the real life application of this or that mathematical idea, notion, or a theorem? Well, the greatest common divisor of two numbers finds its application in modern cryptography, in digital signals processing, in time and frequency of events analysis. For example, if we want to make sure that sooner or later two events, for example, happen at the same time, we will need to compute the least common multiple of the numbers at hand and so on. The notion of the greatest common divisor is also used in load balancing in computer networks. For example, when we decide which of n computers that participate in the network conversation should receive that load of work or the next load of work. The greatest common divisor is also used in modular arithmetic, and it is also used in the process of reducing fractions to the simplest form. So, for example, if we compute the greatest common divisor of two numbers written in the form of a rational number, we cancel it out. So all we get is prime factors in both cases with no common factors in the numerator and denominator. And then, lo and behold, amazingly enough, even a rational number such as, for example, 3/5 can be written apparently as a unique product of primes. But this time, in such a prime factorization of a rational number, we will see powers of prime numbers that are negative. For example, here it's 3 to the positive 1 power times 5 to the negative 1 power. And now in the next few segments, we will understand how does the Euclidean greatest common divisor algorithm preserve the magnitude of the greatest common divisor of two numbers as it weaves its magic. And before we do that, we will look at two honing in examples. Let us say that the mathematical oracle hands us a number which the oracle claims to be a perfect power of 2. And again, 2 is just a simple number. You can pick any other number they want. We would like to keep things as simple as possible, but not simpler. So let us imagine that the mathematical oracle hands us a number and says, look, guys, smarty pants, what is the power of 2, this number? We will take, for example, 16 to be a perfect power of 2. We know that 2 raised to the positive power number 4 yields 16. And again, here we have to be very, very careful, because this experiment and this idea of thinking about a particular power of a positive number works represented as consecutive multiplication only works for whole and positive numbers, because in general it doesn't really make any sense to apply this idea, for example, to real numbers. If we have two real and transcendental numbers, e and pi, what does it mean to multiply, for example, e by itself pi times? It makes no sense. So we need a different notion or different idea of how to think about this type of constructs in general over the set of real numbers that include transcendental numbers, but over the set of positive whole numbers as a rare exception. We can entertain the idea that raising a number to a specific power can be equivalently represented as a series of consecutive multiplications. As such, we have no idea what the mathematical oracle was thinking about when that oracle put that number together, but what we can do is precisely apply this idea as a rare exception. We need to understand that once we step out of the set of whole positive numbers, this is not going to work. But here we can reverse engineer that number by casting out the powers of 2 in an iterative fashion. And this iterative fashion of reducing the problem until the problem cannot be reduced or simplified any further is precisely the spirit of the reduce and conquer problem solving approach, or scope reduction problem solving approach. So here, using the pseudo best programming language of all time, C, what will we write? Well, we'll set our variable n, which is presumably a perfect power of 2, to that initial number 16, and then we'll iterate that number by taking it, dividing it by 2, storing the result back in n, incrementing the power of 2 counter by 1, and running the process until the number is strictly larger than 0. And we think that at the end of this loop, the value that sits in the variable p will tell us what is the power of 2 in this case. Let us see how that will work in practice. On the first iteration, we'll have n is 16 over to 8. 8 is greater than 0. Bam. P was initialized, let's say, to be good citizens, we'll initialize it to 0. So here it becomes 1. The number n is 8, greater than 0. We are back. This if statement, the implicit if statement built into the while loop, evaluates to true. We jump into the body of the while loop. We come over here. 8 over 2 is 4. 4 is greater than 0. P plus plus 2. We jump over here. 4 over 2 is 2. 2 is greater than 0. We're still in the loop. 2 over 2 is 1. So here at this point, once we come out of the loop, p will be what? Will be 4. In the next iteration, 1 over 2 in the integer division. In C, that will be 0. This terminates the loop. We note carefully that this approach is guaranteed to terminate our loop. So the moment we reach 0, and we will reach 0 at some point, that moment terminates our algorithm. And now we carefully count. 1, 2, 3, 4. Bam, p is equal to 4. And here is our answer to the mathematical oracle. The number that you gave us is the fourth perfect power of 2. And again, in general, we play with specific numbers before we come up with an idea. And when someone hands us a number that is a candidate perfect power of 2, we do not know what the specific value is. But if we crank our number through this algorithm of repetitive or iterative casting out 2's from that power, from that usual suspect, this process will terminate when we reach 0. And again, that process, I want to make sure that we're all on the same page and understand that, again, is a chapter that is taken verbatim from the scope reduction problem solving approach. On each iterative process, we reduce the perceived complexity by reducing the size of the problem. We keep the essence of the problem the same, because still in every step we have a power of 2, power of 2, power of 2. Our process terminates, and in some sense we probably do not have the explicit way to climb back up, but at this point the problem is solved. And in the next short segment we will look at the multiplicative copies of 2. Wonderful. This time, let us say that the mathematical oracle said, very well, sunshine, I'll give you a even number this time again, let's say 16, and you are to tell me how many copies of 2 are in there, or how many multiplicative copies of 2 in that number. Here we can conduct a similar experiment, but again, we have to understand this is a rare exception. It only works for positive whole numbers. And in this case, a positive whole number that is even, we can think of as follows. We do not know what the mathematical oracle had in mind when that oracle put that number together, but using our rare exception idea, we can represent that even number as a series of consecutive additions of 2, and by doing so we will know how many multiplicative copies of 2 are in there, in this case 8. How can we do that? Again, what we can do is we can reverse engineer that process that is based on our rare exception model or idea. That is, we initialize our number n to 16, the number of multiple copies of 2 will be 0, and then we run again an iterative process, which is what? Which is again a chapter taken verbatim from the scope reduction problem solving approach. We reduce the problem, or we reduce the perceived complexity of the problem on every step. We preserve the technical essence of the problem at hand until that problem cannot be simplified any further. We solve the simplest problem, and then we roll all the way back up. So here, instead of dividing, we will be doing what? We will be subtracting 2. So instead of dividing, as we did in this experiment, in this problem we will be subtracting. So we consecutively subtract 2 from the current number, assign the value to n again, we increment the number of multiple copies of 2, and we roll through that iterative subtraction for as long as we are above 0 or precisely on 0. How will this algorithm work with a specific computation? Well, I wrote it down for you guys on the right hand side of your screen. The arithmetic over here is quite simple, but it is worth to do it, and maybe you can even do it with your own numbers. But from 16 we subtract 2, we obtain 14. 14 is greater or equal to 0. That's true. This implicit if statement, the value is true, we jump in, increment, and move on, and so on. 14 minus 2 is 12, 10, 8, 6, 4, 2. Then from 2 at some point we subtract 2, we obtain negative 2. Our algorithm terminates. We're not going any further. We're not going below 0. This is 0. And now we carefully count 1, 2, 3, 4, 5, 6, 7, 8. Bam! The number of multiplicative copies of 2 in the number that the oracle gave us is 8, and that algorithm will work with any whole positive even number. Again, we play with the numbers, with specific numbers, to come up with an idea, and now we can take on the Euclidean greatest common divisor algorithm, which again we will work with specific numbers in order to understand and to develop the feel for what is going on with that algorithm. The actual mechanics of the Euclidean greatest common divisor algorithm is very straightforward to describe and very straightforward to understand or comprehend. As we mentioned earlier, the essence of the Euclidean greatest common divisor algorithm comes down to a repetitive subtraction of the smaller number from the larger number, with the possible substitution of the formerly smaller number into the new larger number, as follows. Let us say, for demonstration purposes, we want to compute the greatest common divisor of the numbers 525 and 60, the numbers that we looked at in one of the previous segments. So we want to find out the GCD of 525 and 60, shown over here. As Euclid essentially describes these steps in his book called Elements, we begin by subtracting the smaller number, which is 60, from the larger number, which is 525. On the first subtraction, we get 465. And because this difference is still larger than the smaller or the currently smaller number 60, we repeat this process again. From 465, we subtract 60. We obtain the number 405. 405 is still larger than 60. We repeat this process again. From 405, we subtract 60. We obtain the number 345, and so on. We keep doing repetitive subtraction of the currently smaller number from the currently larger number until, that is, we arrive at this situation shown over here. I will underline this situation lightly so we do not mess up our work. But here we see that if we blindly take the result of the division over here, 45, and from 45 we subtract 60, 45 minus 60 will be negative 15. We'll dip into negative whole numbers, but overall the set of all whole numbers, negative, 0, and positive, has neither upper nor lower bound. If we keep subtracting from negative 15, we subtract 60, we get negative 75, and so on and so on. That means that our algorithm will never terminate. But we want our algorithm to terminate in the finite number of steps. And here we do the following promotion or substitution, if you will. We promote the formerly smaller number 60 to be the new larger number. So in other words, starting from this step over here, the number 60 will play the role of the larger numbers shown over here. And the difference that is now smaller than 60, that is 45, will be promoted into the new number b. In other words, the number 60 now is promoted to be a, or our proverbial a shown over here, and let us say b. And the difference 45 is promoted to be into a new number b. And we keep repeating this process until at some point we reach 0. On the next subtraction of still smaller number, 45, from the larger number, 60, what do we get? We get 15. But we get, and with 15, with respect to 45, what do we have? Well, we cannot subtract 15 from 40. We cannot subtract 45 from 15 because we'll, again, dip into negative numbers. So what do? Another round of promotion or substitution. The formerly smaller now 45 number becomes the new larger number, 45 here, it becomes a, and the difference that is smaller, 15 than 45, becomes the new number b. So we keep subtracting b from a, smaller number from the larger number. On the next round of subtraction, we subtract 15 from 45, we obtain 30. 30 is still what? 30 is still larger than 15, so it is perfectly fine. From 30, we subtract 15, we get another 15. Here, 15 subtracted from 15 gives us 0. At this point, our algorithm terminates, and I put the arrow over here because in the next segment, I'll take the right-hand side of the board. I don't want to write over there. Immediately previous number with respect to 0 is the greatest common divisor of two numbers at hand, and I wrote that fact over here. So the greatest common divisor of the original numbers 525 and 60 is precisely this guy right here. 15 is the answer, and this is the mechanics of how does the Euclidean greatest common divisor algorithm work. This is applicable to all positive numbers, whole positive numbers, and specifically, again, we are looking at the case which honors all the previous constraints that we discussed. Not both numbers are not 0, they're greater than 1, neither one divides the other, and obviously here 60 does not divide 525. 60 times 8 is what? 480, is less than 525. 6 times 90 is 540, is still larger, so no luck, no cigar over here. This is a meaty, substantial, algorithmically interesting case, and this is how the Euclidean greatest common divisor algorithm weaves its magic. And in the next two segments, we will understand why does this algorithm produces precisely, why does it produce precisely the greatest common divisor of two numbers at hand. Now that we understand how does the Euclidean greatest common divisor algorithm work, let us try to understand why does it work and why does it produce the greatest common divisor of two numbers as its output. Back in the middle school, when I was a kid, it was in the mid 70s and early 80s. There was no internet. The only way to propagate information horizontally was by the word of mouth or by the means of a book. So we did not have the internet back then. One of the explanations that I was given about how the Euclidean GCD algorithm worked was not very satisfactory to me. That is why I concocted this particular explanation that I'm presenting to you guys right now. And the idea is this. The textbookish definition of the greatest common divisor of two numbers is all fine and dandy. It is obviously technically correct. It was polished by many scholars, by many people who put certain texts together on the elementary theory of numbers. Everything is fine and dandy. But for me, the definition of the greatest common divisor as is given in textbooks when it's applied to the inner mechanics of the Euclidean GCD algorithm was not really that satisfactory. I think that a better way to look at what the greatest common divisor of two numbers is when it comes to understanding how the Euclidean greatest common divisor algorithm works is the following. For the purposes of understanding how this algorithm works, let us pretend that the greatest common divisor of two numbers is the widest string of primes that are common to both of these numbers. What does that mean? Well, in our case, let's look at the number 525. In the previous segments, we looked at the prime factorization of that number. We wrote it down as 3, 5, 5, and 7. Well, now, of course, we know by manual computation that 3 times 5, or 15, is the greatest common divisor of 525 and 60. But playing around in order to construct an algorithm, let's say, for example, we pretend that we want to invent this algorithm ourselves, we represent this common divisor as the widest string of common primes. In other words, here we leave in the prime factorization of the number 525, we isolate the greatest common divisor as a widest string of primes common to both numbers. And to both of these numbers, the widest string of common primes is what? 3 and 5. When we multiply them together, we get our GCD. That is fine and dandy. But when we isolate this widest string of primes common to both numbers at hand, what do we get? All the other prime factors that did not make it into our greatest common divisor will become, if we want to multiply them out, they will probably become a composite number. In this case, in the case of the number 525, that number will be 35. 5 times 7 is 35. So we can write down the prime factorization of the number 525 for the purpose of understanding how this algorithm works as follows. 35 times x, or 35 times the GCD of the numbers 525 and 60. Likewise, let us massage the number 60 a little bit over here. But remember that its prime factorization was written by us in the previous segments as 2 times 2 times 3 times 5. Again, because we're conducting this experiment by hand, we know that the greatest common divisor of the numbers 525 and 60 is 3 times 5. We leave this greatest common divisor as it is in its expanded form as the widest string of primes common to both numbers. I show these numbers here in red so you guys can see it clearly. 3 times 5. Whatever prime factors of this number 60 did not make it into the net cast by the greatest common divisor of these two numbers, they likely will become a composite number. In this case, it's 4, so we can represent number 60 as 4 times x, or 4 times the GCD of the numbers 525 and 60. So in that representation, it is important to understand that, for example, certain numbers possess certain properties just by themselves, or in isolation. For example, an even number, no matter what it is, has that many multiplicative copies of 2, as we saw in the previous segment. Here, however, these numbers, they make sense with respect to each other. In other words, when the mathematical oracle was putting these numbers together, that oracle did not know that we will decide to compute the greatest common divisor of these numbers. So with respect to another whole positive number, let's say we fix 525, but we pick another number, not 60. It may so happen that there is no widest multiplicative commonality, if you will, between the number 525 and the next number that we pick. These numbers will be called relatively prime because the intersection of the multisets that correspond to prime factorization will be the empty set. No common factors other than 1. So with respect to each other, we can represent these numbers as follows for the purposes of understanding how does the Euclidean greatest common divisor algorithm work. And now that we have that representation, let us basically take these representations and carry them verbatim into our string of computations. What will we see? Well, we will see that the resultant arithmetic is both very straightforward and elegant and beautiful as well. For the first string of subtraction or subtracting the smaller number from the larger number, we get 465. But in our new notation or in our new representation of these numbers, what do we get? 35 units of the widest multiplicative commonality, if you will, or 35 units of greatest common divisor, minus what? Minus 4 units of widest multiplicative commonality, otherwise known as the greatest common divisor of these two numbers. 35 minus 4 is 31. 31 is greater than 4. Beautiful. On the next iteration, where we subtract 60 from 465, we obtain the number 405. But what is that number? Well, that number is represented as 31 units of widest multiplicative commonality x minus 4 units of widest multiplicative commonality. 31 minus 4, 27. 27 is larger than 4. We repeat, and hopefully by now you see I will not spell out all these numbers. I hope you guys see all the numbers clearly. I try to write as large and as bright as possible. 27 minus 4, 23. 23 minus 4 is 19. 19 minus 4 is 15. 15 minus 4 is 11, and so on. Here, however, remember that we had 2 rounds of promotions of formerly smaller numbers into the new larger numbers. So we promoted, in some sense, B into A and then the difference into B. So here is the same thing. When we subtract 4 from 7, we obtain 3x. We cannot subtract 4 from 3 because we will step into the negative numbers, -1, -5, and so on. Our algorithm will never terminate. So here we perform the famous and the understood by us switcheroo, so to speak. The number 4 is promoted, the formerly smaller number 4 promoted into the new larger number, and the formerly larger number is promoted into the new smaller number 3. So now we subtract 3 from 4, we obtain 1. Over here again, the difference is smaller than the current smaller number 3. We perform again the round of substitutions or promotions. 3 is promoted into a larger number, 1 into a smaller, and we keep rolling with this repetitive or iterative subtraction. 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0, bingo. The algorithm terminates right here, and the previously immediate non-zero result, bam, is our greatest common divisor x. And in our case, in our notation, I wrote it over here. I hope you guys can see it. I designated it right here. The greatest common divisor of the numbers 525 and 60 is precisely x, and this number is, let me write down it one more time here, that number is 15. So now hopefully we'll all understand why does the Euclidean greatest common divisor algorithm produces precisely the greatest common divisor of two numbers. And again, as we mentioned it in the previous segments, this is precisely a chapter that is lifted from the scope reduction problem solving approach book verbatim. In our series of subtractions, remember that what we said, that on the one hand, this iterative process or reductive process makes every problem genuinely simpler. And look at this. On every step, the amount of widest multiplicative commonality between these two numbers is genuinely reduced on every step, 31, 27, 23, 19, all the way to 0 on the one hand. On the other hand, this preservation of technical essence of the original problem translates into what? The magnitude of the sought after greatest common divisor of these two numbers remains unaltered. It is one and the same x in every string of subtractions. It travels our greatest common divisor, designated with x, travels through all the series of subtractions, unmolested, so to speak, or in a slightly more fancier or maybe even grown-up mathematical language, the magnitude of the greatest common divisor of two numbers at hand remains invariant under the operation of subtracting of smaller number from the larger number. We witness this fact right here. However, witnessing certain mathematical phenomenon with a specific example is of course good, fine and dandy. It may be a good achievement, but for a solid theoretical explanation, we actually have to switch to some amount of symbolic manipulation. And in the next segment, we will try to explain theoretically why does the magnitude of the greatest common divisor of two numbers survives each and every subtraction in the Euclidean greatest common divisor algorithm. Very good. In the previous segment, we realized how does the magnitude of the greatest common divisor of two numbers percolate through the inner workings of the Euclidean greatest common divisor algorithm. And basically, we feel that we understand that the greatest common divisor of the original numbers, 560, is also present in the difference of these two numbers. In other words, the greatest common divisor of the numbers 525 and 60 is also a greatest common divisor of the numbers 465 and 60. And how did we get 465? We get the number 465 by subtracting 60 from the number 525, and the series of subtractions and preservations of the magnitude of the common greatest divisor is shown over here. So now we want to concoct a possibly theoretical explanation of why is that so. And we begin this by looking at the sum of two numbers. Let's say we have a number d that divides, let me not engage in too much symbolic manipulation, symbolic shuffling, but let's say d divides numbers a and b. What does that mean according to our definition? And d is not 0, of course. Well, it means that for the pair of numbers d and a, there exists a number, let's say qa for quotient, times such that qa times d is exactly a. For the pair of numbers d and b, there exists its own unique quotient here. Let's designate it with b times d. These two relations hold. And then what can we say about the divisibility of the sum of a and b? Well, then the sum a plus b will be represented which way? It will be represented as quotient a times d plus quotient b times d. The d factor is one and the same. We can factor it out and we get qa plus qb times d. And what can we say? Well, the set of all whole numbers, or the set of integers, is closed under the operation of addition. In other words, the sum of any two integers is an integer, or the sum of any two whole numbers is a whole number. And that means that the sum of these two whole numbers is a whole number. And this is precisely the definition of our divisibility in the integers. And that means that for the numbers a, where is it, a plus b, there exists a whole number called qa plus qc, such that this number times d yields precisely the sum a plus b. And if you guys want to play around a little bit, then take your time and look, for example, number 3 divides, let's say, 15, and number 3 divides 48. That means, from based on our tiny theorem over here, that 3 divides 15 plus 48, 48 plus 15 is 63, and 3 clearly divides 63, because for this pair of numbers there exists a whole number called what, 21, such that 21 times 3 is 63, and this is precisely the sum of numbers. Now that we understand that if a number d divides the numbers a and b, then it divides the sum of these two numbers. What can we say about the difference of the numbers a and b? That is awesome. Now that we see if a number d divides both numbers a and b, that means we just proved it divides the sum of these numbers a plus b. But what can we say about the difference of these numbers? Well, we should understand that in this case, the same idea and the same statement holds. If we construct the difference, a minus b, then what will we have? Instead of the plus sign, we will have the minus sign. The d as a common divisor of both numbers will be still one and the same factor. We take it out. So what do we have in the parentheses in front of d? Well, we have a difference of the quotients, the unique numbers qa and qb, that manufacture our numbers based on these relations over here. And what can we say about this difference? Well, it so happens that the set of integers or the set of whole numbers is also closed under subtraction, and that means that the difference of any two integers is an integer, or the difference of any two whole numbers is yet again a whole number. We have a whole number over here, and that is precisely a symbolic representation of the fact that the number d divides the difference of the numbers a and b. Again, if you guys want to play with specific numbers, pick your choices, but using the previous numbers from the previous segment, we have 15, we have 48, 3 divides both. 15 equals 3 times 5, 48 equals 3 times 16. So what about the difference? 15 minus 48 is minus 33, and minus 33 is divisible by 3, evidently, because for this pair of numbers there exists a whole number called negative 11 or minus 11, such that negative 11 times 3 comes out to negative 33. Now that we understand that if a number d divides two numbers a and b, it divides the sum and the difference, what is the next logical step? Well, the next logical step is, in some sense, this is actually enough, but we'll take it a little bit further into the modern age, so to speak. We will see that if the number d divides the numbers a and b, then it divides their arbitrary linear combination. Now that we proved if a number d divides numbers a and b, then it divides their sum and their difference, we can generalize that observation with the statement that in this case the number d must divide an arbitrary linear combination of these two numbers. What does an arbitrary linear combination of two numbers mean in this specific context of integer arithmetic? Well, that means that if in front of a, let me erase this a little bit here, in front of a we put x times, x is an integer, plus y times b. This is precisely an arbitrary linear combination where we can say, for example, let me see it over here, x and y are integers, precisely this. So this formation over here, x times a plus y times b, is what's called an arbitrary linear combination. And what can we say about the divisibility of this arbitrary linear combination of the numbers a and b, each of which is divisible by the number d? Well, we see that the arithmetic does not really get more complicated than what we dealt with before. Here in front of this factor we will have x times, here we'll have plus, and here we'll have y times. So x times quotient a times d, where quotient a is taken from here, plus y times quotient b times d. Quotient b comes from here, from this relation. The number d still remains the same, so what will we have here? We'll have x times qa plus y times qb. And here we just have to say slightly more words with respect to what we said in the previous segment. In other words, the set of integers or the set of all whole numbers is closed under the operation of multiplication as well. What does that mean? That means that the product of any two integers is yet again an integer, or that means that the product of any two whole numbers is yet again a whole number. That means that the product of the whole numbers x and qa is yet a whole number. The product y times qb is again yet a whole number, and we already stated that the set of whole numbers is closed under the operation of addition. In other words, the sum of any two whole numbers, such as this number and this number, is yet again a whole number, and still the whole thing collapses nicely into our symbolic definition of the integer d, of the number d, dividing the numbers a and b. And that fact precisely means that if d divides a and b, then d divides an arbitrary linear combination of these two numbers. And now we're ready to bring this string of consecutive subtractions into the modern age, so to speak, where we can roll up the, let me see, from where to where, up to here. We can roll up this guy right here. 1, 2, 3, 4, 5, 6, 7, 8, right? 8 right here. This whole string over here, we can roll up into one operation that is the courtesy of the wonderful and so-called division algorithm theorem. And now for the last mile, to bring all our discussion home, we step into the modern age and recall the so-called division algorithm theorem. This is a theorem that is usually proved early on in any course on the elementary theory of numbers. And according to that theorem, for any two whole numbers a and b with the assumption that b is strictly greater than 0, there exists, this is the symbol for exist in mathematics. I use it over here not because I want to do symbolic shuffling, but because I don't have much real estate. So for any two integers a and b with b strictly greater than 0, there exist two unique numbers. The number q, which stands for quotient, and the number r, which stands for residue, such that multiplicatively one number can be decomposed with respect to the other in the following way. A is equal to q, quotient, times b plus r, and a very important constraint that many students somehow forget or do not pay attention to, and then they're all sorts of confused, and then they ask all sorts of questions, for example, on Quora, why this, why that. But the way the division algorithm theorem is designed, and the way the whole thing of integer division is designed to work, is that the residue r honors two very and crucially important constraints. First of all, r is strictly less than b by magnitude, strictly less than b by magnitude, and it can be 0. So the values for the residue are very strictly between b less than b and greater than or equal to r. And in that respect, bringing our sequence of iterative subtractions, or the description of how Euclid portrayed that algorithm back more than 2,000 years ago, into the modern age, what do we have over here? We have technically a minus b minus b minus b minus b minus b, and all these minus b's, again, remember the rare exception. When we work with whole positive numbers, we can replace consecutive addition with multiplication. So we carry out minus, we get a bunch of pluses, b plus b plus b plus b plus b. How many times? 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Bingo. 8 times is precisely the number that is produced by the division algorithm theorem. So in other words, 525 can be represented as 8 times 60. I want to make sure that you guys see it. 8 times 60 plus 45. And 45 is strictly less and genuinely less than 60, and it is greater than or equal to 0. So this string of consecutive subtractions can be rolled up into just one line shown over here. 525 minus 8 times 60 comes out to 45. This is the number right here. All this beautiful mess that we made on board over here, all this beautiful mess, this whole thing can be rolled up into one line over here. We see this line right here. Now, what happens next? Well, here we have the proverbial number a, the proverbial number b, and our residue r. This is the quotient q. On the next step of our Euclidean GCD algorithm, what do we have? Well, we have our formally smaller number b, and by the way, again, the division algorithm is designed, it is precisely and strictly larger than the residue. So what do we do here? Automatically, no questions asked, maybe, or if maybe, if not, if whatever. We always promote the number 60 into the new larger number. So b is promoted into a, and r, the residue, is promoted into b. It now becomes the new smaller number, and 60 becomes the new larger number. And we repeat the whole thing again. by using again, the mechanics of the division algorithm theorem. Here, how do we represent 60 in terms of 45? Well, 60 is equal to 1 times 45 plus 15. If we subtract the b-related term from 60, what do we get? We get 15 as the residue. And again, because the way the division algorithm mechanics is designed, this residue will be always less than the number b. So we again promote 45 into the new larger number. The residue promoted into the new smaller number. Here, however, 45 minus 3 times 15 is 0. Bam! 0 terminates the algorithm. The number that immediately precedes 0 is the GCD in question. So here in our string of consecutive subtractions, what do we have? Okay, we compress 8 consecutive subtractions into one line over here. We compress this line over here, 60 minus 45, into here. It becomes one line over here. Sorry, this line right here. And this line is what? 1, 2, 3. So these 3 lines right here are compressed into one line over here. They produce 1. The algorithm terminates, and 15 pops out as the greatest common divisor of the numbers 525 and 60. And I recommend, I don't have enough room over here, but you guys should really write down, for example, this experiment, repeat this experiment with x. What do we have over here? 525, so that will be 35 minus what? So let me do, maybe I can do it for you guys over here. So we will have 35x's minus what? 32x's, right? 8 times 4 is 32, so that will be 35x minus 32x will be 3x. And then again, we do a switch, which is shown over here. 4 minus 3 is 1, and then 3 minus 3 comes out to 0. So we recommend that you write down, okay, maybe let me do it, okay. 35 times x minus 32 times x comes out to 3x. Then we have 4x minus 3x comes out to what? Comes out to 1x. And then finally, again, what do we have in our division algorithm notation? We'll have 3x minus 3x comes out to 0x. So 3 times x minus 3 times x comes out to 0x. Terminating point, bam, 1x is our guy. Everything converges beautifully, all courtesy of the so-called division algorithm theorem, in which, again, the residue is designed to be genuinely and strictly smaller than the number b, and it can take the values that are greater than or equal to 0. And in case when the residue is precisely 0, then we say that, again, the one number divides the other one without the residue. So now the final question that I want to address is the following. Why does the Euclidean greatest common divisor algorithm terminate with precisely 0? You can think about it on your own, and in the next segment I'll share my ideas with you guys. So why does the Euclidean greatest common divisor algorithm terminate and terminates precisely at 0? I see 3 fundamental reasons, but if you guys think that there are more, please don't be shy. Use the comment section to this episode, share your ideas and your thoughts. But the first reason why the Euclidean greatest common divisor algorithm terminates is because overall we're dealing with integers. Specifically, all we're doing is integer arithmetic. That means that, for example, if d will designate, for example, let's say here, if the number d is the greatest common divisor of the numbers a and b, then we know that by the linear combination theorem that we proved in the previous episode, we know that d must also divide what? We know that d must also divide an arbitrary linear combination of the numbers a and b. And one of that linear combinations could be precisely what we have over here. For example, a minus q times b. That linear combination must be divisible by any divisor of numbers a and b, and including the greatest common divisor as well, because when we proved our linear combination theorem, we didn't make any special assumptions about the nature of the divisor. So the greatest common divisor will divide the numbers a and b and their arbitrary linear combination, including this one, a minus q times b, where the number q is produced courtesy of the division algorithm theorem. But that linear combination is what? Precisely, this linear combination is precisely the residue from the same division algorithm theorem. Conversely, let's say some number c divides our number b and the residue r. What does that mean? Well, again, if the number c divides the numbers r and b, it divides their linear combination, including this one right here, this linear combination, q times b plus r, where q again is a courtesy of the division algorithm. And what is that number? Well, that number is a, apparently. And because this number over here is an arbitrary divisor of the numbers r and b, that means that with respect to the greatest common divisor, that number must be less than or equal to d, according to our definition of the greatest common divisor. And that hopefully shows that, yes, indeed, the number d, the greatest common divisor of the integers a and b, is also the divisor of the numbers of b and r. So one reason why the Euclidean greatest common divisor algorithm terminates is because we are dealing with integers altogether and fundamentally. The second reason exactly comes from this constraint over here, which means that on each and every step, the size or the complexity of our problem is genuinely reduced due to this strict inequality over here. The residue on every step of the Euclidean greatest common divisor algorithm becomes strictly smaller than the currently smaller number b. If we look at this algorithm through the lens of consecutive subtractions, the Euclidean style, okay, it takes us a little longer, but we see a genuine decrease on every step. 31, 27, 23, 19, 15, and so on. If we look at this algorithm through the lens of the modern division algorithm theorem, then over here the residues go what? 45, 15, bam, 0. So a genuine decrease. So that's number two. The third reason, which altogether explains why does the Euclidean greatest common divisor algorithm terminate precisely with 0, is the fact that all the distances that are involved over here in this case are strictly finite. In other words, b being positive, again later on in most textbooks this will be generalized into any number altogether, but the number b, the distance from the number b on the number line to 0 is finite, and that means that the set of all possible residues that we can encounter along the way, courtesy of the division algorithm theorem, is also strictly finite. This residue cannot decrement forever and cannot spill over into the negative whole numbers. It must terminate with 0, and that is precisely the three arguments. We're dealing with integers. The size of the current problem is genuinely reduced on each iteration, and the greatest common divisor of two original numbers survives all these reductions, and the residues in the reductive process of computing these residues due to the division algorithm theorem cannot decrease forever. There is a hard lower bound, which is 0. Lastly, hopefully this explains more intuitively why does the Euclidean greatest common divisor algorithm work and produce the greatest common divisor of two numbers. If we look at it through the scope reduction problem solving approach, if you guys have a better idea or even better, more see-through, more transparent, more intuitive explanation, I'm all ears. Be my guest. Use the comment section to this video. But no discussion of the mechanics of the Euclidean greatest common divisor algorithm is complete without some automation. Yes, what you just saw on your screen was a way to automatically compute the greatest common divisor of two numbers written by me in the best programming language of all times. See, I kept this code on your screen for about 5 to 7 seconds. That should be plenty of time. If you guys want to take any action on it, put this video on pause. You can copy the code. It's not very complicated. C is quite straightforward programming language, and if you will be doing it, you probably know that without me, but just in case, once you save, for example, that code in a file called gcd.c, you will come out to the terminal, and in the terminal window you will type in GCC for the GNU compiler or whatever compiler you use. You should probably, if you use your own, you probably know better than I do how to compile your program, but with the GNU compiler you will type in GCC, then you'll give it a space -G to include the debugging symbols in your executable, -O for the output, give it your favorite name. I say GCD space, give it a space, and then the name of the disk file gcd.c. The compilation will go through. This compilation will produce the executable image called GCD, and you invoke it as follows: /GCD space, for example, 525 space 60, and the number will pop on your terminal. This is it for the mathematical problem S2E23, and we will look at the new challenge next. Wonderful. Do not forget that we're still studying the mechanics of the scope reduction or reduce and conquer problem solving approach. For those who missed the explanation of how that problem solving approach works, I suggest that you find the season 2 episode 21 and listen to our explanation. But in the lightning round, the whole idea of applying the scope reduction or reduce and conquer problem solving approach to the process of solving this or that technical problem is to observe that if it is the current difficult problem you cannot solve, then there exists a simpler related problem that you can or cannot solve. Applying this logic recursively, we create a chain of reductive simplifications of the problem, and we drag the technical essence of the original problem through all these simplifications. If we can solve the simplest problem, then we try to gain the insights into what is going on during the solution of the simplest rock bottom related problem. And then we step up all the way, gaining more and more insight, and eventually we solve the original difficult problem. So here in the next challenge, it will be mathematical problem S2E26. You are invited to evaluate the following Riemann integral, the integral that runs from C to, let's say, 2C. That was the question that was given on Q1 of these fine days, and the integrand looks as follows. The integrand looks as follows: x over square root of x squared plus cx minus 2c squared dx, where c is, let's say, greater than 0. Again, in words, the definite integral with the boundaries of integration that run from c to 2c. C is strictly greater than 0, strictly positive real number. The integrand looks as follows: x in the numerator, and in the denominator we have square root of x squared plus c times x minus 2c squared. Again, you are invited to solve this integral using precisely the scope reduction problem solving approach. We're not interested in anyone slugging this integral into one of these automated bots or what have you, or integral calculators. There is nothing to be gained. On this channel, we're trying to learn how to think like a mathematician. We're trying to learn how to think out of the box. Precisely, there is a clever and beautiful mathematical idea that sits over here. It all comes down to the scope reduction problem solving approach. Try to find it. Good luck. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the mathematical problem S2E26.